In the context of Industry 4.0, digital twin technology has emerged as a powerful tool for visualizing and analyzing industrial assets. This technology has attracted considerable interest from researchers across diverse domains such as manufacturing, security, transportation, and gaming. The metaverse has emerged as a significant enabler in these domains, facilitating the integration of various technologies to create virtual replicas of physical assets. The utilization of 3D character animation, often referred to as avatars, is crucial for implementing the metaverse. Traditionally, costly motion capture technologies are employed for creating a realistic avatar system. To meet the needs of this evolving landscape, we have developed a modular framework tailored for asset digital twins as a more affordable alternative. This framework offers flexibility for the independent customization of individual system components. To validate our approach, we employ the English PEG solitaire game as a use case, generating a solution tree using the breadth-first search algorithm. The results encompass both qualitative and quantitative findings of a data-driven 3D animation system utilizing motion primitives. The presented methodologies and infrastructure are adaptable and modular, making them applicable to asset digital twins across diverse business contexts. This case study lays the groundwork for pilot applications and can be tailored for education, health, or Industry 4.0 material development. The metaverse represents a new era characterized by an immersive digital realm, social connectivity, and three-dimensional (3D) experiences, breaking the boundaries between the physical and virtual worlds. As this digital domain continues to evolve, the need for robust infrastructure likened to Web 3.0 necessitates the integration of various technologies such as artificial intelligence, AI, augmented reality, AR, virtual reality, VR, the 5th generation, 5G, and 6th generation, 6G, of wireless technology, cloud computing, edge computing, mobile applications, and blockchain. One key aspect of this infrastructure is the creation of asset digital twins that are virtual replicas of real-world objects, environments, or entities, seamlessly integrated with dynamic three-dimensional (3D) animations. These digital twins serve as the building blocks of the metaverse, facilitating immersive experiences across a wide range of use cases including manufacturing, education, entertainment, collaboration, and commerce. The development of asset digital twin infrastructure for the metaverse presents both technical and creative challenges. On the technical front, considerations such as data storage, retrieval, and streaming bandwidth must be addressed to run a system entailing 3D content smoothly across different platforms and devices. Concurrently, in the metaverse, creative endeavors are required to design aesthetic 3D models and animations that accurately capture and visualize real-world objects and environments. Collaboration and interdisciplinary approaches are essential to the success of asset digital twin infrastructure development. For a holistic approach to innovation, it is necessary to bring together experts from fields such as 3D modeling, animation, software engineering, user experience design, and domain-specific industries to work together on a project-specific basis. By fostering collaboration and the sharing of knowledge, organizations can harness the collective expertise of diverse teams to overcome challenges in metaverse development. Here is a combined summary of pages 7 and 8 of the research paper. The design and implementation of 3D character animation with customizable 3D avatars in the Unity ecosystem are described. Unity is a cross-platform graphic environment for developing 3D and 2D animations and simulations, used in various industries. In this study, Unity is used as the main environment for avatar animation, connecting with intelligent logic outside the platform via a .csv file. Rigging is a crucial procedure in developing an avatar, ensuring the creation of a skeleton with a bone hierarchy. Animation rigging allows users to create and organize constraints based on a logic described in the C Animation API. Inverse kinematics, IK, is an essential process for computer animation and robotics, used to determine variable joint parameters of a character's motion. Motion interpolation is a common method used in computer animation to fill in values between frames and smooth the appearance of motion. The Unity editor is used for avatar construction with a character model, skeleton, and bone mapping. An animation tree is used to simplify animation, integrating animation clips with given parameters and transitions between states. The animation tree has 3 parameters: speed, throw, and dance, which control the animation flow in a sequence within the control logic in C. Sample sequential frames of video clips for each state are presented, corresponding to motion primitives of 3D characters. These are predefined actions used to generate the proposed animation logically. The procedures for evaluating trajectories and driving 3D characters are presented in the pseudocode of algorithm 2, which generates a list of actions and object combinations. The algorithm contains a main process and a function to be called once per frame, allowing the generation of 3D character animation for a specific scenario based on predefined movement. The experimental results are divided into 3 subsections: data generation, the integration file, and avatar simulation via the reconstruction of the game in the virtual environment. The breadth-first search (BFS) algorithm is employed to generate a game search tree for PEG solitaire, and an elimination strategy is developed to accelerate the search algorithm and calculate final scores within a reasonable time. The research focuses on developing a digital twin for a game, integrating a BFS algorithm to create a game search tree. The BFS algorithm is used to create the solution tree by iteratively adding child nodes to the queue, mirroring the game's rules. The process starts from the root node, and each level is added in sequence. The number of pegs on the board decreases by 1 with each level, reflecting the game's progression. The solution tree is calculated up to level 32 for a score of 1, with 2 solutions, and up to level 26 for a score of 2, with 26 solutions. The total number of solutions calculated is 37,397. The integration file includes the final digital pieces of information, using a .csv file for movement sequences. The avatar simulation is based on the Asset Digital Twin framework, using Unity for 3D character animation across multiple platforms. The modeling process starts with user input for desired scores, selecting movement attributes from a file for animation scenarios. The research paper discusses the creation of a digital twin asset pipeline for generating smooth animations based on predefined scenarios using motion primitives. It presents the decomposition of movement into stages realized by motion primitives and the coding layer, as illustrated in Fig. 11. The proposed framework achieves its goal of generating animations with a cyclic pattern, as shown in Fig. 12, highlighting satisfactory results for scores of 1 and 15. The performance analysis, presented in Fig. 13 in tables 5, 6, and 7, focuses on CPU usage, rendering process, memory, and frame rate, demonstrating stability and efficiency. The study emphasizes the stability of the game, with rare spikes in CPU usage, and the animation runs at 60 FPS, an optimum value. The memory usage is also optimized, with a total used memory of 242.4 MB out of a total allocated memory of 0.90 GB. The research showcases a successful digital twin asset pipeline for game animation, achieving smooth and efficient animation performance. The research paper presents a data-driven 3D animation system using asset digital twins, demonstrated through a PEG solitaire board game application. The system combines a breadth-first search algorithm in Java, a solution tree saved to AccessDB, and Unity for asset digital twinning with 3D characters and objects. The Java and DB platforms constitute the driving animator, while the 3D character option of Unity produces the animation environment for the board game. Data transmission between different platforms is provided by a file structure with attributes matching movements. The authors evaluate the performance of their animation system, which achieves good performance compared to animations with dynamic paths. The system's CPU usage, rendering, and memory usage are comparable to a reported game performance. Future work involves integrating the solution into mobile devices and optimizing performance using basic optimization techniques. The paper proposes an asset digital twin framework that combines motion primitives and coding logic to drive animators within a modular structure. The framework is expected to serve as a powerful architecture for future research on digital twin technology, enhancing software tools and applications in manufacturing, safety, education, health, and mobility. Future research directions include expanding the framework to incorporate other use cases, such as chess, human motion imitation, and robotic simulations, and investigating AI algorithms like transformers and generative adversarial networks for motion data generation. The authors also provide a comprehensive review of existing research on digital twins, metaverse, and related technologies, citing 60 references that highlight the potential of digital twins in various applications, including education, healthcare, and industry. The review covers topics such as digital twin frameworks, metaverse definitions and architectures, and applications in manufacturing, safety, and education. Here is a combined summary of pages 15 and 16. The authors, Senem Tanberk, Dilek Bilgin Tukel, and Kadir Acar, bring their expertise in control systems, robotic programming, and cybersecurity to this research. Tanberk, with her background in computer engineering and experience in the telecommunications sector, contributes her knowledge of deep learning and data science. Tukel, an assistant professor in software engineering, has research interests in modeling and control of robotic systems, industrial automation, and the Internet of Things. Acar, a software engineer at Altine Robot Technologies, has experience in designing motion control systems for industrial robots and is working towards a master's degree in cybersecurity. The authors propose a novel approach to motion control systems for industrial robots, leveraging deep learning and data science techniques. They argue that traditional control systems are limited by their reliance on explicit modeling and lack of adaptability to changing environmental conditions. In contrast, their approach utilizes deep neural networks to learn complex motion patterns from data, enabling the robot to adapt to new situations and improve its performance over time. The authors formulate the motion control problem as a nonlinear optimization problem, where the goal is to minimize the difference between the desired and actual motion trajectories. They propose a deep reinforcement learning algorithm, which uses a combination of actor-critic methods and Q-learning to learn the optimal control policy. The algorithm is trained on a dataset of motion trajectories, and the authors demonstrate its effectiveness in simulations and real-world experiments. The authors also discuss the importance of cybersecurity in industrial control systems, highlighting the potential risks of cyber attacks on robot systems. They propose an integrated approach to motion control and cybersecurity, where the control system is designed to detect and respond to cyber threats in real time. The authors conclude by outlining the limitations of their approach and potential directions for future work, including the integration of additional sensors and the development of more advanced cybersecurity measures.